Welcome! Today we're going to tackle a really interesting question. How do you get middle schoolers to think like actual professional engineers? We're diving deep into something called the Flameless Heater Challenge. So let's just jump right in with the big question. How do you teach a kid to think like an engineer? I mean, really get into that mindset. It's not about memorizing formulas from a textbook, that's for sure. You start with a real, hands-on problem and a box full of pretty simple, everyday stuff. We're talking plastic containers, Ziploc bags, aluminum foil, and some basic chemicals you could find at a hardware store. This is where it all begins. And that, of course, brings us to the heart of this entire project, the Flameless Heater Challenge. Okay, so the mission for these student engineers seems pretty simple on the surface, right? Design a homemade heater that can warm up food without any kind of flame. But the devil is always in the details. It has to be cheap, it has to be effective, and maybe most important of all, it has to be safe. And this is where the real engineering thinking kicks in. It's not just a creative free-for-all. See, every engineering project is built around two key ideas. Criteria, those are the goals you need to hit for it to be a success. And constraints, those are the strict rules and limits you absolutely have to follow. The real trick is to succeed within those rules. Now, take a look at how specific these rules are. This is what makes it a real challenge. The heater must get the food into a temperature window of 40 to 47 degrees Celsius. That's the effectiveness part. And it has to do it in around 15 minutes. The total weight has to be less than 700 grams. But here's the big one, the real kicker. The materials for the heater have to cost less than $3. That is a tough constraint. Yeah, let that sink in for a second. $3. That's it. A limit like that forces some incredible creativity. It makes students think really hard about every single material they use, just like a professional engineer has to do on a multi-million-dollar project. So, the students have their mission, they've got their rules. What's next? Do they just start grabbing stuff and putting it together? No way. This is crucial. Before you build anything, engineers plan on paper. Engineers really work with two different kinds of models. First up is the paper model. That's for planning. It's where you map everything out, calculate your costs and mass, and, super important, get safety approval before you've wasted a single bit of material. Then, and only then, do you build the physical prototype. And that's all about testing. Does this thing I dreamed up on paper actually work in the real world? And believe me, this isn't just doodling in a notebook. Just look at this actual student design. They've calculated the exact amounts of chemicals they need, they've listed out the cost and mass of every single component, and get this, they've even drawn a model of what's happening at the particle level to show how the heat energy moves from the reaction to the food. I mean, that is some serious scientific planning right there. So once that paper plan gets the green light from the teacher, it's time to build what we officially call a prototype. And a prototype isn't meant to be the final polished product. Nope, it's an early version built for one reason and one reason only, to be tested. And now we get to the fun part. The part everyone's been waiting for, actually building that first prototype. So you might be wondering, how do you test a food heater in a classroom without, getting spaghetti all over the place? Well, they came up with a pretty clever solution. Instead of real food, the students use water bead soup. It's just a mix of these hydrated water beads and water, and it actually mimics the texture and the thermal properties of a meal really, really well. The chemical reaction they're using is great for generating heat. It's a mix of copper sulfate and aluminum in salt water. But there's a catch. There's a hidden danger that every single team has to account for in their design, or things could go wrong. And here it is. That reaction produces hydrogen gas. And hydrogen gas, as you probably know, is flammable. So if you sealed the container completely, that gas would build up pressure, and it could pop, splashing hot liquid everywhere. And that's exactly why one of the most important safety constraints is that the container has to be vented. It's a perfect example of a chemistry principle directly influencing an engineering design. Okay, the prototypes are built. The safety precautions are in place. It is time for the moment of truth. And testing isn't just, hey, does it feel warm? Oh no, it is a strict scientific protocol. First, you weigh the entire thing. Then, you mix the reactants and hit the stopwatch. You measure the temperature of that soup every 5 minutes, on the dot. And all of that data gets carefully recorded in something called a design testing matrix. It's all about collecting good, clean, reliable data. And this is what success looks like in data form. You can see it right here. At the start, time 0, the temp is 22 degrees Celsius. But look, after just 10 minutes, it hits 45 degrees. Boom! Right in the middle of that target zone. They did it. They met the effectiveness criterion. So does that mean the students whose heater hit the target temperature won? Well, not exactly, because getting the right result on the first test isn't really the finish line. And that brings us to the biggest question of all. What truly makes someone an engineer? You know, this chart from their classroom really says it all. Engineering isn't some straight line from a problem to a perfect solution. It's a loop. It's a cycle. You define the problem, you brainstorm and develop a solution, and then you optimize it. That means you test, you look at the data, you learn from what worked and what didn't, and you go right back to the drawing board to make it even better. So when you boil it all down, what did these students really learn? Well, here are the big takeaways. They learned that you have to test your designs to figure out how to improve them. They learned that paper models and physical prototypes are both super important, but for totally different reasons. They figured out that clear, precise instructions are critical. And maybe most of all, they learned that to solve really complex problems, you have to work together. And that really brings us to the core philosophy of this whole lesson. It's captured perfectly in this quote. The goal isn't just to build a solution, it's to learn the cycle of designing, testing, and optimizing. And that right there is how you teach someone to truly think like an engineer.